and we're looking at the effect of all the broadening terms, both in terms of the HETP and the corresponding plate count. So this is what the number of plates per meter looks like as a function of flow rate on this particular column. And we get our best result, our absolutely best result, with the K prime of 0. And as we increase the K prime, the plates per meter drops, and drops a lot. And as we keep increasing the K prime, it gets smaller and smaller until it essentially reaches a final asymptotic value with a K prime roughly of 20, where if you make the K prime any bigger, things don't get any worse. But this is the plates per meter. And what controls the resolution is not the plates, but the effective plate number. The resolution is equal to the square root of the effective number of plates times your selectivity factor. Remember, the effective number of plates incorporates the retention factor of the compound. So if we now make a plot not of plates per meter, but effective plates per meter versus the flow rate, we see an entirely different behavior. Here is K prime of 1. As I said the other day, there's no point in plotting K prime of 0 because the effective plate number when K prime is 0 is 0. Anything times 0 is 0. And as I increase the K prime, I see an increase in the number of effective plates per meter. So this is K prime of 3, then K prime of 10, and then K prime of 20. And it doesn't do you much good to increase the K prime any further than this because you've reached the largest effective number of plates per meter that you're going to get. So what I'm telling you is that the decisions you have to make are better made in terms of the effective plates per meter because that's the factor that controls the resolution. And this is frequently why we have to use a somewhat thicker film than you might want to use, because if you have an exceedingly thin film, your retention factors might be just really low, and although the plates per meter looks good, the effective plates per meter is not going to look very good. The next thing I want to look at is our reduced plate height at the minimum in the Van Deemter curve, and then look at the reduced velocity at the optimum velocity. And we're going to look at it versus retention factor and as a function of the dimensionless, the reduced film thickness. So there's the curve, reduced plate height versus retention factor for a rather thick film. Theta is 10. As we use a thinner film, the reduced plate height decreases. That's good, because it means the HETP is lower, which means that you've got more plates. And as we go down and down and down, we eventually get to a K prime of 0. And at a K prime of 0, we have our minimum value of the reduced plate height at the optimum of the Van Deemter curve. So this is the best you can do in terms of reduced plate height. I'm sorry, I said K prime is 0. I meant I meant theta of 0, where you have essentially an infinitely thin film of stationary phase. Now, how you get an infinitely thin film of stationary phase that has a retention factor of other than 0, that's purely hypothetical. It's ideally what you want, but of course you can't get it. The next thing to consider is the effect of the film thickness on the reduced velocity, and this is the optimum reduced velocity. So here's the curve for a film thickness of 0, then a thicker film thickness, and of course what it does is it lowers the optimum reduced velocity. So the thicker the film, the slower you have to go to be at the optimum reduced velocity. And thicker, 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 it just gets worse and worse and worse. Obviously, you want to work at a high optimum reduced velocity because that will get the separation done in the least amount of time. So there's a lot of trade-offs that you got to make to really do open tubular chromatography, or indeed HPLC, to do it fast and also to maintain high performance, meaning high resolving power. This is a quantitative statement of what I just showed you graphically, but for the specific case of an infinitely thin film of stationary phase, here's the retention factor, here's the optimum velocity and the minimum plate height, and for this diameter capillary, this is the number of plates per meter. And you can see as the retention factor gets bigger, the optimum velocity goes down and the minimum plate height goes up. Just as a point of information, if somebody asks me, what is my reduced plate height going to be at the minimum, it's going to be about 1 to 2 in gas chromatography. If I've got a decently coated, well-prepared column. And so it's going to be 2 times the radius of the tube. So the smaller the radius of the tube, the more plates you're going to have, the more per unit length, or the more plates you're going to have on a column of a given length. The smaller the radius of the tube is, the faster the absolute velocity will be. Reduced velocities, you know, if we don't do something stupid like work at a very low K prime, your reduced velocity is somewhere between 2 and 3 at the optimum. So it's pretty easy to guesstimate what your optimum flow rate should be. Corresponds to a reduced velocity of something between 2 and 3. Okay, in my notes there's another section called separation impedance. It's not that it's unimportant, it's very straightforward. I think you need to read it over in my notes. With that, I can get on to packed beds now, where life gets a little different because we do not have the advantage of having an exact solution to the mass transfer problems because of the complexities of the packed bed. So what we'll talk about the rest of today is begin to get into what goes on in a packed bed in somewhat greater detail than what we did when we were in the random walk model. And we'll lead off by talking about pressure. Whoops. We'll lead off by talking about pressure, Reynolds number, and turbulence. And the situation in a packed bed is really very different than in an open tube. It's a good bit easier, That sounds like it's good, but it's actually bad. It's a good bit easier to get into turbulent flow in a packed bed than it is in an open tube. That's not necessarily good, because it means that you're going to have to use more pressure to get the fluid through the column. And usually in a packed bed situation, you're struggling to overcome the pressure limitations of the column. To understand what's going on in a packed bed, we have to look at a number of different kinds of velocity. And among them are the so-called superficial velocity, which is the easiest to compute, and then things get more and more difficult as we go through these other velocities. And perhaps today I'll get to talk a little bit about what we call external mass transfer, which is resistance to mass transfer from the moving phase to the outside of the particle. And then eventually we'll talk about resistance to mass transfer inside the particle, which we call internal mass transfer. Okay, so there's an open tube. We're going to pack particles in this tube. In liquid chromatography, this tube typically has an analytical scale of liquid chromatography. This tube typically has dimensions of 4.6 millimeters diameter. And it's packed with particles that are really small compared to the diameter of the column. These days, 5-micron particles are large particles. That's the diameter of the particle. These went out about, I'd say, 10 years ago, where particles on the order of 3-micron diameter became pretty common. And then a few years back, maybe 5 years ago, with the advent of sub-2-micron particles, particles on the order of 1.7 to 1.8 micron diameter came into play. Somewhere between here and here, we crossed a very serious boundary. The instrumentation available up to about 5 years ago had a pressure limit of about 5 to 6,000 psi. Roughly 400 bar was the maximum possible pressure that could be generated. When this sub-2 micron barrier was breached, 400 bar, 5,000 psi just didn't cut the mustard. It simply wasn't enough to operate the column properly. And a number of companies started to introduce very high pressure systems on the order of 800 bar, then 1,000 bar, then 1,200 bar, and I think currently 1,200 bar is the maximum that's available. So the column is packed with these small particles. That means there's several thousand particles across the ID. So what I draw here is a ridiculous representation of what's really there. But we've got tightly packed particles. Now, the volume of the unpacked tube, that's just pi r squared L. This volume is not what's important. There's a number of volumes that are important. The total volume of the tube is occupied, first of all, by the volume of the solid material. Now, the phase is solid, but that doesn't mean it's not porous. So we have to also incorporate the volume that's inside the periphery of the particle. That's called the internal volume of the particle. And then we have to include the volume outside the particle. And that's called V sub E. So this is the internal volume, and this is the external volume. And there will be fluid in both of those volume elements. Now, the external volume is equal to the external porosity times the total volume of the unpacked tube. So this is the external porosity. This represents the spaces between the particles. So if I have two particles touching like this, it's the space in the cusp. So it's the fluid here. In a well-packed HPLC column, this number is typically less than about 0.42 and greater than about 0.38. If you have to stick in a number, 0.4 will do. Now, the volume inside the particle depends upon how porous the particle is. The particle may have no porosity at all. It may be just a solid particle, altogether no space in it, in which case its internal porosity would be 0, and that's the end of the story. But if we have internal porosity, that internal porosity multiplies the volume occupied by the particle. Now the volume occupied by the particle is going to be 1 minus the external porosity of the bed times the total volume of the tube. So if you will, 1 minus epsilon E times V naught is the volume occupied by the particle, and this porosity is based upon the particle size. So it's the volume inside the particle divided by the volume occupied by the particle. If the particle were a sphere, that would be 4/3 pi r cubed. So that's our internal volume. And we would write that as EI times the volume occupied by the particles. There are velocities that correspond to most of these different kinds of volume in the system. And frequently in the literature, you'll see people talk about the superficial volume. The superficial velocity. Engineers like this one. The superficial velocity is just the volume of the unpacked bed, of the unpacked tube, divided by the flow rate. The nice thing about the superficial velocity is it's related to two things that are really easy to measure. The volume of the tube, if it's a cylinder, is pi r squared L. The flow rate is the volumetric flow rate. It's easy to measure. So, did I do that right? No, that's not right. Superficial velocity. That's right. That's the superficial velocity. It's the flow rate divided by the cross-sectional area of the open tube. Sorry about that. The interstitial velocity is the superficial velocity divided by the porosity of the bed, of the outside of the bed. This is also called the interstitial porosity. And so this is called the interstitial velocity. Now this is a very important number because it is actually the rate at which the mobile phase progresses down the column as it sweeps past the particles, not inside the particles, but just past the particles. So this is really the velocity scale that controls chromatography. It measures how fast a molecule of anything will be moving, on average, outside the particle. Now, the actual velocity of a chromatographic zone of unretained stuff if we're dealing with porous particles, is equal to the superficial velocity divided by the total porosity of the bed. The total porosity of the bed is very easy to calculate. E total, epsilon total, is the interstitial volume plus the internal volume divided by the total volume of the unpacked tube. And in the previous overhead, we came up with equations for VE and V internal, and I'm just going to make believe we do the algebra. So the total porosity is the porosity outside the particles plus the net porosity of the particles and the volume that they occupy. Now, if you have non-porous particles, the internal porosity is 0. This term doesn't matter. And so the total porosity is equal to just the porosity outside the particles. So this number ranges from 0 on up. In gas chromatography, because the pressures are not very high, they will sometimes use particles with very, very high internal porosities, maybe even 0.8. The pressure is so low that you're not going to break the particles. But if you try to do HPLC with a particle whose internal porosity is 0.8, the particles are just going to be crushed immediately. There's a maximum that we can deal with in LC because of the high pressures, and because the pressures have gone up. Now, the particles have had to be redeveloped so that they can handle the high pressure. But a typical value of an internal porosity of an HPLC particle, of a fully porous HPLC particle, will be about 0.4. So if we put in my estimate of epsilon E of about 0.4, we come up with a total porosity of the bed on the order of 0.6 or less. And if we use epsilon E as the bottom end of that for a totally non-porous particle, then your total porosity is somewhere between 0.4 and 0.6. So it's not hard to estimate the dead volume of the column. Now, the particles used in HPLC and in gas chromatography, well, no one does what I'm going to tell you about in a second. So the particles in HPLC and in GC come in two flavors. There's the fully porous, and then there's the superficially porous, where this is a solid core, and then on the outside of it there's a thin shell. The chromatography takes place in the thin shell. These obviously don't have as much internal porosity as a fully porous particle. It depends on exactly who you buy it from. So I really can't tell you a good number to use for the porosity of this kind of particle. It's greater than 0. It obviously has to be less than fully porous. I think it depends on how thick the shell is and so on and so forth. So you have to look at the manufacturer's literature to come up with an answer for that problem. Okay. The velocity of of an unretained species is easily determined from the length of the column and a measurement of the dead time. To measure the dead time, you have to inject something which is not retained, but is small enough to fit in all the pores of the particles. In gas chromatography, we typically use a very light gas, something like methane will do. If you're working at higher temperature, propane probably could be used. In liquid chromatography, it depends a lot on the nature of the liquid chromatography that you're doing. In, say, reversed phase, LC, typical dead markers are uracil, thiourea. Both are commonly used. In ion exchange chromatography, obviously you don't want to use something that's ionic, and you don't want to use either a cation or an anion, because on an anion exchanger, cations will be excluded from the inside of the pores, and vice versa on the other side of the ion exchange. But if you're using water as a mobile phase, something like acetonitrile, uncharged molecule would probably. In normal phase chromatography, it depends on exactly what the mobile phase is as to what you would use as a dead marker. It's pretty hard to come up with good dead markers for normal phase chromatography. Okay, the total volume, the dead volume, would be the sum of BE and BI, and that would simply be the flow rate times the dead time of the column. We can relate the interstitial velocity to the zone velocity of an unretained species just by keeping careful track of our volumes, and that works out to be this number. Since this is a positive number and we're adding it to 1, the interstitial velocity is greater than the zone velocity. The zone velocity includes the fact that molecules fit inside the particles. The interstitial velocity says all we care about is the velocity when they're outside the particles. So this has got to be higher than that with a given flow rate. Now, in size exclusion chromatography, SEC, we have a different situation. In size exclusion, some of the molecules fit in all of the pores. Some of the molecules are excluded from all the pores, and some of the molecules go in some of the pores. So we have to take into account the fraction of the pores which are accessible to a specific size molecule. And so the zone velocity for a specific size molecule depends upon the fraction of the volume that's accessible to it, and that works out to be this is the velocity of a molecule that fits in some of the pores. This is the velocity of a molecule that fits in all of the pores. Phi is the fraction of the pore volume that's accessible to a particular molecule, to a particular size molecule, and that has to be between 0 and 1. Now our friend, the reduced velocity in liquid chromatography and in packed bed gas chromatography is based upon the interstitial velocity, although there's some people in the literature who don't use the interstitial velocity. They use U sub m instead. And these people obviously have not read Gittings's papers. We will only base V, the reduced velocity, on the interstitial velocity. We'll multiply by the diameter of the particle unless we're using an open tube, in which case we'll use the radius of the open tube. And then we divide it by the diffusion coefficient of the solute molecule that we're talking about in the fluid outside the particles. And there's one other term which I'm going to introduce now, although I'm not going to use it now. We'll use it a little bit later. And that's something that resembles a retention factor. And this is the ratio of the fraction of my solute inside my pores, but not chemically retained, just fits in certain pores, but it's not retained in the stationary phase, relative to the volume that's outside of the pores. It's like a retention factor, but it's a steric exclusion retention factor, if you will. And this will come into play when we get into the details of the HETP, and it's a real unfortunately confusing factor in the following sense. Even if a molecule is not retained in the stationary phase, if you have a porous particle, a certain fraction of your solute will be inside the support particle, and a certain fraction will be outside the support particle. So it has to diffuse to get into that interior space, even if it's not retained. So if it's K prime or 0, it doesn't mean that it doesn't go inside the particle. It will if its phi value allows it to go inside any of the pores. And we can relate the use of m of that size molecule to the interstitial velocity divided by 1 plus k naught. And you see it's playing the role of a retention-like factor because of the relationship between this and this through the k naught in the denominator there. So we have to worry about these different velocities when we're talking about mass transfer, and which one we worry about depends upon what kind of mass transfer we're talking about. I now want to get into issues related to pressure. And the point of this slide is to show you where turbulence starts in a packed bed. This number here is a so-called friction factor, and I'll tell you about it in a minute, what it is exactly. But this is a plot of the friction factor versus the Reynolds number in a packed bed. Now, the Reynolds number in a packed bed is defined a little bit differently than the Reynolds number in an open tube. The Reynolds number in a packed bed is based on the superficial velocity. Now this is a linear velocity. This has units of length per unit time. It's based upon the diameter of the particles packed in the bed. If the particles are spheres, this is easy. If the particles are cylinders or cubes or stars or whatever, it gets a little bit nastier. In which case it becomes what's called the hydraulic diameter of the particle. And we're not going to go there because we're not going to use cylinders or spheres, anything with spheres, because spheres are the best things to use. And then it depends upon the kinematic viscosity. Now, in a completely unpacked tube with smooth walls, the transition from laminar flow to turbulent flow takes place at a Reynolds number of about 2,000. In a packed bed, that's completely wrong. The transition takes place when this plot of friction factor begins to roll over. And that begins to happen somewhere about a Reynolds number of 10. So turbulence starts at a much lower Reynolds number in a packed bed than in an open tube. Now this might bother you. You think that a lot of LC is done under turbulent flow. It just ain't so. The kinematic viscosities of liquids are really high, number one. Number two, the particles that we use in LC must be rather small particles. I just told you about the use of 1.8 micron particles. If you put in reasonable numbers here, the Reynolds numbers hardly ever get much above 0.1 or 0.2, which means that we're really under laminar flow. And not only that, but the Reynolds numbers that we work at in LC are referred to as creeping flow. Creeping. That means extremely low flow. And I'll show you some pictures next time about what creeping flow really means. Okay, so if I mess around with the friction factor appropriately, and I'm in laminar flow conditions, I can calculate my pressure drop. And this factor of 150 here is an empirical factor. It looks like it's been calculated from theory. It's not. This is the result of averaging together about 80 zillion papers This is a dimensionless 150. It has no units. This is called the Cosini-Kármán equation. The pressure is proportional to the viscosity. Certainly you know by now that the viscosity of liquids is way higher than viscosity of gases. I mean, gases was hundreds of micropoise, liquids were fractions or hundreds of millipoise or a few centipoise at most. Proportional to the viscosity, proportional to the length of the column to the first power, proportional to the flow rate to the first power under laminar flow conditions. Inversely proportional to the square of the radius of the column. If we put linear velocity up here instead of flow rate, that would cancel out that radius dependence. All that really matters is the linear velocity. It's not the flow rate, it's the linear velocity that matters. And here's the kicker. It depends inversely on the square of the particle diameter. Now, over the history of LC, the particles have gotten smaller and smaller and smaller. And every time we drop the particle diameter a factor of 2, the pressure drop needed to push stuff through those beds goes up a factor of 4. And this is what accounts for the increase in the pressure from 400 bar to 1200 bar over the past few years. The change from 3 micron particles to 1.8, 1.7 micron particles has crossed that barrier, and we've had to increase the pressure. Why is this a big deal? Try making something that will deliver an absolutely constant flow rate at a pressure of 1200 bar without leaking. It's difficult. It's challenging. The other factor here is the interstitial porosity, and it's got this funny dependence, but this has been checked very carefully, and this 1 minus epsilon squared over epsilon cubed dependence is quite real, and consequently how the particles are packed has an appreciable effect on the measured pressure drop. I don't know why I repeated that. So here's a plot of pressure. This is in thousands of psi. I'll remind you that 1 atmosphere is 14 psi, about. This is in a 4.6 millimeter ID column. Here's flow rate, not linear velocity, because what we set on our pump is flow rate. You don't set the linear velocity. The pump doesn't know what the diameter of the column is yet. They'll figure out how to make it know that soon. And I've done this for 3 representative columns, 3 micron, 5 centimeter, 5 micron, 10 centimeter, and a 10 micron, 25 centimeter. I picked those numbers because the plate counts are about the same. And you can see that the pressure drop here is a lot higher than the pressure drop there, even though it's a shorter column. Why do you think we would do this? I said the plate counts are the same. It's all about time. It's all about time. This is about twice as fast as this, and this is about twice as fast as that. And 1.8 microns are about twice as fast, maybe a little bit more than that, of the 3 micron columns. And the 1.8 micron columns are typically 30 millimeters long, not 50 millimeters long. here's the, I believe this was with water as the mobile phase, and this is with helium or hydrogen as the mobile phase. And now this is in PSI, not 1,000 PSI. It's a vast difference in the pressure drop. You don't need a pump to deliver the pressure in gas chromatography. You've got to have a pump to deliver the pressure in liquid chromatography. Okay, so now we're about ready to get into where does the HETP come from. And for that we have to look at our friend, this element of the column. We're going to use a small element, delta Z. It's going to be a packed bed. We're going to account for how material gets into that element and how material gets out of that element. Obviously it can move in by diffusion and it can move out by diffusion. It can be pushed in by convection or it can be pushed out by convection. So we're going to add up both of those transport processes. So the rate at which stuff accumulates in this element delta Z is the net effect of convection in and out and diffusion in and out. So the way we compute convection is the velocity times the area, which is flow. We're going to assume an incompressible fluid so that the flow into the cell and the flow out of the cell is the same. It's exactly the problem I had you work last week. The difference from last week's problem is that what gets transported in is the concentration at this point, Z minus delta Z. And what gets transported out is the concentration over here at Z. And the same thing applies to diffusion. It's the cross-sectional area available for diffusion times the diffusional flux in minus the diffusional flux out. You put that all together and you have the rate of accumulation. We have a stationary phase, so the rate of accumulation is based upon the change in the number of moles in the mobile phase plus the change in the number of moles in the stationary phase. I'm going to add all this stuff up. I'm going to let delta Z go to 0. Well, I get the delta Z going to 0. Mobile phase, this is the accumulation in the stationary phase. This is the volume of stationary phase per unit length of column. This is the cross-sectional area per unit length of column. So that's my accumulation. That's my net transport. I let delta Z go to 0. And I wind up with this partial differential equation. And this is my diffusional flux. If I write it in diffusion and then cancel out common terms, this is my net transport equation into and out of that element of volume. And so we see we've got 4 terms. And I'll put here, but this is not very different from what we did in the capillary column a few days back. But this equation has to be solved to get the HETP.